Thank you. Well, good evening all. A very warm welcome to the Astronomical Society of Edinburgh's final online meeting for this season, and an especially warm welcome to our guest speaker, Professor Isobel Hook, and I'll introduce Isobel in more detail later on. As we get started, I'd just like to completely reveal this amazing background image. This is our reigning image of the year, as chosen by our members. This is the Elephant's Trunk Nebula, presented by Eros Tang. It's easy to see why it was such a popular choice, but if I recall, there was plenty of strong competition. So I'm Neil Martin, the latest president of the Society, and this is a particularly exciting evening for me, my first meeting as president. And what an amazing meeting it promises to be. But first, back to Earth with some basic housekeeping. If you're joining us on Zoom, then please can you ensure that your microphone is muted for now? Thank you. And we have a beautifully simple agenda this evening. I have a brief summary of what's coming up soon, and then I will properly introduce our special guest speaker for the main talk this evening. So let's begin with a quick look ahead to the near future with some dates for your diary. Tonight is obviously Friday the 20th of June, and this is our online meeting for this month. Next Monday, the 23rd of June, the Vera C. Rubin Observatory First Look live event will be hosted by the Royal Observatory of Edinburgh at Dynamic Earth. I look forward to seeing many of you there, and listen out for further references to this new facility later on. The following Monday, 30th of June, is the deadline for the current Image of the Quarter competition, 23:59 that evening to be precise. Our current Image of the Quarter holder, David Brett, will be judging. And here's a reminder of the detailed image of Jupiter which won David that accolade. So if you'd like to follow in both Eros and David's footsteps, then get your entries in before the end of this month. But be sure to follow the instructions in the latest newsletter. We enter our summer break in July and August, so there are no hosted meetings. We do, however, have some suggested activities for you. You could review our website and the members area for all the great content. You could watch the YouTube recording of the June meeting for Sean's sky and summer advice. You should keep a lookout for any incoming newsletters, although Mark's also on a very well-deserved break, so they won't be as regular as normal. And of course, you could practice using your equipment in non-darkness and brush up your image processing skills, ready for the next Image of the Quarter iteration. And if you're in the North Berwick area between mid-July and mid-August, possibly visiting the Fringe by the Sea event, you'll have the opportunity to view the ESA photography exhibit, previously on display at Dirleton as part of the Solar Walk project. And here's a reminder of this excellent display, which was put together by Dan Arnold. In summary then, there's plenty to do, so it's not really a break. And whilst these are only suggested activities and not specifically set as homework, I'm very much looking forward to hearing your stories of what I did on the holidays when we return in September. And talking of September, we'll be back with a bang. It's an action-packed month. Our meetings include our main meeting at the Augustine United Church, which is a hybrid meeting on Friday the 5th of September, and that's also open to the public. Our guest speaker that evening is Professor Brad Gibson, who'll present liquid mirror telescopes, wave of the future, or just a ripple. Do love a good pun. On the 10th of September, we have our online imaging and observing group session, and that one is for members only. So if you're interested in getting involved in those, then join up. On the 19th of September, we have our next online meeting, also open to the public, We don't have a speaker confirmed for that as yet, but we'll have information on that soon. Also in September, in other events, we have a collection of open doors events at the beginning and end of the month. So on 7th September, there's a gala day at the Collective Gallery, City Observatory, Calton Hill, where we'll be helping with some guided tours and providing info on the Society. At the end of the month, on the 27th September, at the same venue, there's a Doors Open event, where again we'll be running some guided tours and providing info on the Society. That same weekend, yes, we need to be in both places at once. There will be a Doors Open event at the Royal Observatory of Edinburgh on Blackford Hill, where we'll be hopefully doing some solar observing. Hopefully we get a day like today. And again, providing info on the Society and answering any questions from the general public on astronomy. So lots to look forward to in September. Having taken a look ahead, now it's time to focus completely on the rest of this evening. And it's my great pleasure to formally introduce our guest speaker for this main event, Professor Isobel Hook. Isobel is a professor of astrophysics at Lancaster University. She gained her PhD from the University of Cambridge and went on to do postdoctoral fellowships at the University of California, Berkeley, and at the headquarters of the European Southern Observatory in Germany. She then held roles connected with the Gemini Observatory, including a 2-year position at the Gemini North Telescope in Hawaii. Following this, while based jointly in Oxford and Rome, she worked on the European Extremely Large Telescope project. And in 2016, she moved to Lancaster to lead a new observational astrophysics group there. Her current research is focused on the use of Type 1a supernova for cosmology. And as a member of the Supernova Cosmology Project, she was involved in the discovery of the accelerating expansion of the universe and was awarded a share of the 2007 Gruber Cosmology Prize and the 2015 Breakthrough Prize in Fundamental Physics. She's now involved with planning a new generation of surveys to understand dark energy. And she was recently awarded the Caroline Herschel Medal jointly by the Royal Astronomical Society and the German Astronomical Society for her contributions to cosmology and to astronomical instrumentation. Now, as astronomers, we love a good search. Many of the things that we search for are faint or dim or dark. So this talk is sure to tick all the right boxes. Please give a warm welcome to Professor Isobel Hook. Isobel, I'll hand over to you.
Yes, thank you very much for that very kind introduction. Well, it's a great pleasure to be speaking to you. I spent some time working in Edinburgh at the Royal Observatory on Blackford Hill, and I have great, fond memories of it. And some of the work I'm going to be talking about was work done there, as you will see later on. So I'm going to start sharing. Let's see. That one. Okay, now I hope that's the right way around. Can you see the main title?
You need to switch displays again, I think. Yep.
That. Okay. All right, let's do that. And I just get my pointer. All right, so hopefully you can see that okay. All right, so I'll just get started then. So yes, I'm going to talk about my work on supernovae and the search for dark energy. And I'm just, this image that you're looking at now, a little taster, is from the Euclid telescope, a recently launched mission. And I'm going to come back to that later and show how that fits into the whole science area. So just to give you first a sort of overview of what dark energy is and why it's such a big problem. So it really is one of the biggest mysteries in physics, dark energy. So it came about, or it was sort of introduced as a term, because we knew that the expansion of the universe is accelerating. So what's shown here on the right is a diagram, sort of history of the universe, starting from the Big Bang down at the bottom left. And as time goes on towards the top right, we see the universe expanding quite quickly initially. Then it sort of coasts for a bit under the influence of the gravity of the contents of the universe. But then sometimes sort of not too distant past, around sort of this point, I don't know if you can see, it says you are here, the expansion seemed to actually speed up again and get faster and faster. And so that's the accelerating expansion that we have evidence for, and I'll explain why we think that's true. So we have measured that acceleration, but we do not understand at all what's actually causing it. And it's that mysterious thing that's causing the acceleration that's been given this name dark energy. And that is pretty much, it summarizes our sort of ignorance of the whole, the cause of this accelerating expansion. We just had to come up with a new name for the thing that causes it, and that's what we call dark energy. So in this talk, I'm going to try and explain the evidence we've got, why we think the universe is accelerating, and what the current sort of thoughts are on what dark energy could be, and what we're trying to do next, try and understand more about it and what really is causing this acceleration. So to do that, I'm going to just explain a little bit about how we go about measuring the expansion of the universe. And just in sort of basic way to explain it, I'm sure you would understand, is that you just want to measure the size of the universe at different times. And you can think of that as kind of blowing up a balloon, but rather than thinking of the whole universe as being a balloon, you have to think of the surface of the balloon. So imagine that you've got galaxies painted on the outside of a balloon, and you blow up the balloon. All the galaxies will move apart from all the other galaxies, but there's no real center to that expansion. And that's the sort of analogy of what we think of the way to think about the universe expanding, that everything's expanding from every other part of the universe, but there's no center to that expansion. So you kind of have to translate this balloon idea, this surface of a balloon, into a three-dimensional surface that's expanding. So you need another dimension really to visualize it. That's the problem. So that's what we're trying to sort of measure, this expansion. And it turns out that measuring the size of the universe, the relative size of the universe, is actually pretty straightforward. And we can use the concept of redshift, which I'm sure you've come across before, and possibly, is often explained as a kind of Doppler shift because of things moving apart. But actually, when you're talking about cosmology, it's more correct to think about the expansion of space itself. And with this balloon analogy, it's quite clear how it works. So if you imagine a light wave going across the surface of the balloon, which is our universe, so light propagating across the universe, as the universe expands, the space expands, and the wavelength of the light that's crossing the universe also expands. And so it gets shifted from shorter wavelengths to longer wavelengths, or towards the red end of the optical spectrum, if we're considering optical light, which is why it's called a redshift. So this is the cosmological redshift. And it's an incredibly simple way to measure the relative size of the universe, because you can measure this shift of certain emission lines, for example. So I've got that on the next slide. So for example, these are they're spectra of 5 different galaxies here shown lined up on top of each other. So this is where the light from a distant galaxy has been passed through some sort of dispersing instrument, a prism or something like that. And you can see the characteristic wavelengths of particular ions or atoms in the material in those galaxies. And you can see the same sorts of patterns appearing in each of those galaxies, because they contain similar, mostly hydrogen, but also other, similar elements in their emission. But you can see that they're all shifted. Those lines are shifted relative to each other by different amounts. And that shift is very easy to measure. You can just, almost put your cursor down and see what wavelength those emission lines are appearing. And the amount that they're shifted from the wavelength you'd expect in a laboratory is a very direct measurement of how much the universe has expanded from the time the light left those galaxies to when it arrives at us. And I think that's really amazing. I think we measure redshifts all the time, but when you think about what you're actually measuring, the expansion of the universe, it's really quite mind-blowing, I think. So that's quite simple, actually, measuring the relative size of the universe. It turns out the tricky bit is knowing the timing. So remember, we need to know the size of the universe at different times, and it's the times that turn out to be difficult. So to get the time when light left these galaxies, we need to know basically the light travel time, so how far away they are. And that means measuring their distances. And as you probably know, measuring distances in astronomy generally is very difficult. I mean, if you look at this lovely image, it's just an excuse really to show this pretty image from the JWST, but you can see some objects that are a lot brighter than others in this image. And if I asked you to tell me which you think are closer and which are further away, you'd probably guess that the brighter ones are the ones that are closer, and you might well be right, but you don't really ever know whether a little tiny faint dot there or faint smudge is a bright galaxy that's a long way away, or just intrinsically a very faint galaxy. So what we need is some sort of type of object where you know its intrinsic brightness, and then you can use the apparent brightness on the sky to tell you the distance. And there are several classes of these types of objects where we do know their intrinsic brightness, and collectively these are known as standard candles. And the type of object that I'm most interested in using are type 1a supernovae, a particular type of supernova, which we believe we know the intrinsic brightness of quite well. So I'll just start these two little movies going if they'll work. No, they won't, because I have to get rid of my pointer to do this. No, it's not going to do it. Sorry about that. I can't start my movies without. I can get rid of that. Okay, now I can. Let's do that. Okay, so there's two movies here showing two possible scenarios of how type 1a supernovae form. But basically, we think that they are the explosion of a white dwarf star, which is already the end point of stellar evolution. The star's already died, but if it accretes more matter from a companion and is pushed over a certain fundamental mass limit, called the Chandrasekhar mass limit, it can no longer support itself by electron degeneracy pressure, which is the special state that these white dwarfs are in. And they can't support themselves anymore, and they undergo a thermonuclear explosion that completely destroys the white dwarf star. So because we think that they always occur at this same mass limit, and they always completely destroy the star, we expect that the total energy released in these explosions is always pretty much the same. So we think that they're pretty good standard candles, that they have a fairly standard intrinsic brightness. And so we can use them to measure distances by measuring their apparent brightness on the sky. And type 1a supernovae are particularly good. They're uniform in their peak brightness. That's the key standard candle quantity, but they're also very bright. So they can be used at very large distances, at cosmological distances, to measure the distances to very distant galaxies in which they lie. So that's the sort of principle. They are very good standard candles, and they're not actually perfect. And I'll come back to that very briefly at the end. But we think we can calibrate them very well, so that they are very useful for cosmology. So with this idea, the problem then becomes finding lots of supernovae at different distances from us, so that we can measure the size of the universe at different times, effectively at for supernovae at different distances. So we've got to find lots of type 1a supernovae. And the problems here is that the supernovae are unpredictable and rare. And we typically expect about one supernova per galaxy per 100 years. So you'd have to wait. If you're monitoring one galaxy, you've got a long wait to see a supernova there. Let me see if I can start this. There we go. This is just a time lapse of one particular supernova exploding in its galaxy over a period of several months. So you can see it get brighter just about. It's the object circled in red there, and then fading away slowly. And that whole process takes a couple of months, something like that. So that's a relatively bright one, but the ones we're interested in for cosmology are pretty faint because they're just a lot further away. So they don't look quite as spectacular as even that. But the real breakthrough in this, making this whole project possible, this idea of measuring the cosmological expansion with supernovae, it came about when large digital detectors for astronomy became commonplace, because that meant that you could observe a large area of sky in one go. And so you'd be monitoring many, many galaxies, not just one at a time like this. So you could have thousands of galaxies in your field of view, and effectively monitor those, and then you have a good chance of finding a supernova, or actually several. So before I carry on, I just wanted to mention this. There's one particular amateur astronomer, I don't know if you've come across him before, Reverend Bob Evans, who worked in Australia. And he was famous at the time when he was doing this most actively for finding supernovae by eye, visually. He found 40 between about 1981 and 2005. And that at the time was a world record for the most supernovae found by an individual. And he was doing it by memorizing galaxies. So he was moving his telescope around, pointing at individual galaxies. He had thousands of them, and he could actually remember what they looked like, so that if he came back to them and looked again and something had changed, he would know, and he would be able to say that, well, that's probably a supernova, and he would report them. And it was really a remarkable achievement. So memorizing galaxies, the way they look, that's not something that we can really rely on now as our technique. And what we do now, as I mentioned, is use large digital detectors, as I said, to monitor many galaxies. And this is one example of a distant supernova, just circled in that white circle there, appearing in one image. It's not there in the original image, and it appears. So if you blink between the two, you can just about see a little smudge appearing. That is one of our distant type 1a distant supernovae. Anyway, we don't know the type at this point, but and what we actually do, rather than blinking images, is to take a series of images at one epoch, and then come back a few weeks later, take a second epoch, and subtract the images. And because they're digital, it's very easy to do that cleanly. Well, not that easy, but it can be done cleanly. And so when you subtract them, you see candidate supernovae like this one here. And then we'd have to go and confirm the type with a spectrum. And I'll mention that again in a minute. So that's the sort of principle of how we go about finding supernovae for cosmology. So just before I go on and tell you how, what the results look like, I wanted to just go through where things stood before the discovery of the accelerating expansion of the universe, and why people were interested in this at the time. And I've just got this graph of the size of the universe against time that I'm going to fill in. So at the time when this all started, which was sort of early 1990s, the Big Bang model was well established. And if you have a Big Bang in a model of the universe, obviously that sets the universe off with a motion at the start. And then if you think that there's only matter in the universe, which is what people believed at the time, there's really only three things that can happen in the history of the universe. One is that you give it this initial kick, and it will just collapse back on itself, rather like throwing a ball up in the air and it just falls down again. If there's enough matter to a gravitational attraction, so enough matter to cause gravity to be strong enough to pull the universe back together again. That's one scenario. Another is that there isn't enough gravity or enough matter in the universe. Then after that initial kick, the universe will just keep expanding forever, never collapse back on itself. And then there's a critical situation in between where the universe has just the right amount of gravitational strength in it, or enough matter to make it just, it'll expand, never actually turn around, never actually collapse, but it will sort of asymptote to a steady size. And for various reasons, it was generally assumed that middle case, that perfectly balanced case, was the truth. And the main reason for that was that the theoretical model called inflation predicted that the universe should be flat, spatially flat, which means that the total amount of energy in the universe should be equivalent to this critical value. And so if you believe that there's only matter in the universe, then matter has to make up all of that energy density. And so it has to have exactly the critical density to it. So I'm using this symbol omega matter just to represent the relative amount of matter in the universe relative to that critical matter density. So don't worry too much about that, but that's the thing we were trying to determine. So which, at the time, it was generally accepted that there was only matter, but how much was really not known. And so the experiment really that people wanted to do at the time was to work out which of those three scenarios is the truth. Start my pointer again. Here we go. So which of those three lines would be the truth? So the idea was to measure supernovae, and I've just drawn them on the middle line there because that was the general expectation. that we would find supernovae lying somewhere on there, and we'd be able to tell how much matter there is in the universe. And in all cases, you can see that the curves bend downwards as time goes on, and that's just because in all cases, there's only matter in the universe. The matter is slowing the expansion of the universe down by the pull of gravity. So in all cases, you would see a deceleration in the expansion of the universe. So the team that I later joined, called the Supernova Cosmology Project, was set up to measure this cosmic deceleration and to find out which of those three scenarios was the truth of our universe. And this is on the left here, a nice picture from 1991, before I was involved, showing some of the first members of the Supernova Cosmology Project. So second to left is Saul Perlmutter here, who went on to win the Nobel Prize for this work. And Gerson Goldhaber here, I'll show one of his plots later, which is quite nice to see. And then on the right, that's a more recent photo of some of the members of the Supernova Cosmology Project. And there's me right there. So this group set out to try and measure the cosmic deceleration, and the scheme that they came up with, and this was nicely set out in a plot by Saul Perlmutter. There's rather a lot going on here, but I'll just take you through it. And the basic idea was that in new moon, which is represented by that dark circle at the top there, you take a whole series of images covering a nice large area of the sky, so you've got thousands of galaxies in your images. Then you wait a few weeks to the next new moon, where it's nice and dark again, take the same images covering the same area of sky, and then subtract them, and you should see some nice supernova candidates appearing. That's what's shown in this kind of middle cartoon there. And then, because you know the date when you're going to take that second set of images, you could schedule in advance some follow-up observations to measure the light curve, the rise and fall of the supernova. That's shown here. And what we actually need to measure is the peak brightness of the supernova. That's the standard candle quantity. So it's quite important that this follow-up observations were ready to go and pre-booked, because we needed to be able to measure the peak brightness after the discovery of each supernova. So that was one of the big breakthroughs, really, realizing that you could schedule when the supernovae were going to be discovered, because we were covering a large enough area that you could guarantee that you'd find some. So that was one thing that happened. And then similar sort of timing to that, we would have scheduled follow-up observations to obtain spectra to measure the redshifts. And usually we'd get that from the galaxy emission lines that I showed you earlier, the shift in the galaxy emission lines. So then we've got the redshift, we've got the peak brightness, and the final thing we need also from the spectrum is we confirm the type of supernova, because you only really want the type 1a supernovae, and you can confirm that by certain features in the spectra. So then we've got everything we need. And the SCP Supernova Cosmology Project found their first supernova in 1992. It was the most distant supernova known at the time, at a redshift of about 0.5. So the universe had expanded by about 50% since the light left that supernova and arrived here. And this was really a proof of concept. It showed that they could find supernovae and they could use them for cosmology. So every supernova that's found could be used to give you one measurement of that matter parameter. But obviously each one gives you quite a large error bar, so you need to find lots of them to build up a robust answer. But it showed that you could do the experiment, and they wrote this paper, and you can see here the title of the paper was the supernova at this redshift and implications for measuring the cosmological deceleration. So they were still thinking at that time they were going to find deceleration. So on they went. So soon after that, they started bringing together different telescopes and actually doing subtractions from images taken with one telescope to images taken with a different telescope. That's a little bit harder, but it can be done. And it meant that there was more observing time available, and they were able to get the sample up to 7 supernovae. And then around 1994, I moved to Berkeley in my first postdoctoral position and joined in this survey. And around the same time, possibly even more significantly, a second high redshift supernova search team was formed, which was led by Brian Schmidt and Adam Rees. And this was very interesting because they were a group of people with a lot of experience in astronomy, whereas the group that I had joined in Berkeley had actually come from particle physics originally, and were treating this much more as an experiment. whereas the astronomers had quite a different attitude to it, and it was all very interesting. And it's really, I've written competing team there was formed, and it really was a competition. There was quite a lot of excitement as who's going to get the result first. But at the same time, we were often meeting each other and seeing each other at the same telescope. So it was quite a nice and very exciting time. So around this time, we both teams started using this camera called the big throughput camera, which was a large format array, digital array mounted on the Cerro Tololo telescope in Chile. So we had now an even wider field of view and better weather, so we could really accelerate excuse the pun, but the whole experiment really started to accelerate at that point. And I'm just showing some images here that I took around that time of my colleagues, Alex Kim and Peter Nugent, and this lovely fleet of VW Beetles that they had as the observatory cars at this observatory in Chile. Yeah, so I've just got a few other little things just to show you from that time, but the site there in Chile was absolutely beautiful. The sky is so clear and dry and stable. You can just see the sky there looking absolutely stunning above the telescope. And a lot of my own observing, as well as doing the imaging observations in Chile, I was very involved in the spectroscopy observations, which were mostly done at the Keck telescopes in Hawaii. And so these two telescopes on the left here are the Keck 1 and Keck 2 telescopes. They're both 10-meter telescopes, and you really need that sort of aperture to get the spectroscopy of these very faint objects. And it's a very high site, so it's quite a strange place to work. At 4,200 meters, you really feel the effects of the altitude there. This is actually, that last one was not my photo. It's a much more professional looking photograph. This is my own photo from that time. We were using one of these Keck telescopes. The other one was still being built at the time. And you can see also in the background the Subaru telescope, which is the Japanese 8-meter telescope also being built. So it really was, we were very lucky to be using these telescopes really as soon as they were available. It was absolutely fantastic. And then after a few years, they set up the remote observing, so you could observe from almost sea level in Hawaii. So you still had to go to Hawaii, so it wasn't that bad, but you didn't have to go to the altitude. So that was also a very nice experience traveling to do that. So there's a lot of observing goes on. And then finally, in about 1997, there was this big surprise started to emerge from these results. And so what I'm showing here is a graph that Gerson Goldhaber, who I mentioned at the beginning, showed in one of our group meetings. What he's got here is on this graph paper, each sort of centimeter square is one supernova, and each one gives you a measurement of this matter parameter, omega matter, that I mentioned. And remember, we were expecting a value of around 1. So if I show you here, there's 1. And the supernovae were definitely not agreeing very well with omega matter of 1. They were coming out at much lower, on average, at much lower values of omega matter. So something around 0.3, sort of here-ish, was the value that was being found. So there was something unexpected coming out here. And so there was a lot of testing and checking and making sure nobody had made a mistake anywhere. But eventually it was agreed that that was the result. And this is actually what was published. This is the graph from the paper that shows the evidence for the accelerating expansion of the universe. So what's shown here is, this is called a Hubble diagram. So we've got the brightness of supernovae on the vertical axis with the magnitude system, so fainter ones going up, and redshift on the horizontal axis. And our supernovae are the red points here, and the yellow ones are some nearby supernovae from the literature that kind of anchor this Hubble diagram. And then plotted on that are various lines for what you would expect the brightness of a supernova to be for different contents of the universe, different models of the universe. And the second to bottom one was the expectation at the time. That's the universe which contains only matter and nothing else. And the best fit to the data just doesn't really fit. The supernovae are generally fainter than you would expect for that previous model. And that's, you can see that, and I think my eye just in that figure, and that is the evidence at the time that the universe was accelerating, because what it shows is that you can't just have matter in the universe, there has to be something else. And that other thing has to have the effect of making supernovae or any standard candle further away than you would have expected for a given redshift. So something's pushing the universe apart. And the simplest explanation is Einstein's cosmological constant, which is a kind of has this property of kind of a negative pressure on the universe. I'm going to come back to that a bit later on, but that's why it's written lambda here as the other option in addition to matter in the universe. So when you put those two things together, that about 30% of the energy density in the universe is mass, and the other 70% has to be this other thing with this negative pressure type property, those two things together give you a measurement for deceleration that's negative. So that's the evidence that the universe is actually accelerating. So if I go back to that graph that I showed you earlier on with the size of the universe against time, it's not quite the same axes as the last one, but this is the graph I showed you before and what we expected to happen. What we actually found was not that, but something more like that, the black line. So the universe starts to slow down originally, but then at some point just takes off. So it's like, you're throwing your ball up in the air, and it sort of almost starts to come down, but then just sets off. And it really is that weird that we don't understand what's causing this. A very strange observation. So we know that the universe is accelerating now, and this won the Nobel Prize for Physics in 2011 after, again, many more checks and other results confirming this. It also solved one other problem. I don't know if I've got time to mention that, but if you put these graphs together now, instead of joining them together at the Big Bang, because it's now we're actually making these measurements, what happens is that it tells you that the Big Bang actually happened longer ago than we thought previously. And that solved one of the other problems that was around at the time, that measurements of the oldest stars were coming out older than what we thought the age of the universe was on this red line. But with the black line, now you've got more time. So that was also a very nice thing. And generally people, when these results came out, accepted it very quickly. So I mentioned the Nobel Prize. So this is my iPhone picture. I got to go to the ceremony. I took a picture of the ceremony. So we've got the Swedish royal family and the Swedish Academy of Sciences here behind them, and the Nobel laureates here. And it was an absolutely wonderful occasion. Highly recommended if you get a chance. So that was kind of the I think the result that the universe is accelerating, I think, was accepted generally, but the cause of it really isn't accepted or isn't known still. And I mentioned earlier that we just termed this thing dark energy. It's possible that it could be Einstein's cosmological constant. It has the right mathematical form. So Einstein actually introduced this constant because he thought that the universe was static at the time when he was developing his theories. But he knew that there was gravity in the universe that would pull it together. So to counteract that and make the universe static, he put in this extra term, which has this kind of balancing, almost negative gravity kind of effect to it. Then when he found out that the universe was not static, and when Edwin Hubble found that galaxies were moving apart, he called the introduction of this lambda term his biggest blunder, but it actually matches our measurements extremely well, the form of this lambda term. But there are problems with this. It doesn't quite solve everything. So one of the problems is that the actual value, that the sort of size of this energy density, is strangely similar to the value of the matter density, but it's not exactly the same, and it's not. And why should it be the same now when we measure it now and not at different times in the universe? So that's called the coincidence problem. And perhaps the bigger problem is that there's really no natural explanation for this term. What is this energy density that's everywhere in the universe? So that's probably the bigger problem. So that really motivated further studies and many more supernova experiments and surveys that are still going on now. So one of those I was involved in sort of 2000s was called SNLS, which I won't go into much detail here, but the general idea was to just keep observing the same patch of sky over and over again and keep churning out supernovae on a much larger scale than we'd been able to do before. And when you do that, we could get the sample up to a few hundred rather than 40 or so, which is what we had before. And I mentioned that I was working in Hawaii at one point. So this is the instrument that I'd gone to Hawaii to install, called GMOS. And GMOS was actually built in Edinburgh at the ROE, or assembled there anyway. So that's what I was doing most of the time when I was working in Edinburgh, was working on testing this instrument in the laboratory, and then we took it to Hawaii to install it and start using it. And I used it for my own science as well as doing observations for other people. So I was doing some supernova observations with GMOS, which was very nice. So after projects like the Supernova Legacy Survey and other similar ones, the sample of supernovae for cosmology was up to about 740 rather than 40 from the original discovery. So this is another Hubble diagram with the brightness against redshift again. And the data fits exactly what we'd found before. So the accelerating expansion was confirmed. Einstein's cosmological constant still fits really well, beautiful match to the data, but we still don't know what's actually the physical explanation behind that constant energy density. And then just in the last year or so, there's been a very interesting development. So this sample of supernovae has now grown a bit more. There are about 1,500 now in single samples of supernovae, and more when you put them all together. And the first hints are now emerging that the properties of this dark energy are perhaps changing with time. And if that turns out to be true, so it's just borderline whether the results are significant now, but if it turns out to be true, that means it can't be the cosmological constant causing the accelerating expansion, because that would be constant. It wouldn't change with time. So this is really interesting. And this has really focused everyone now that there's a really big target now for the next generation of projects. And there's fortunately some very important projects about to start, which I'll just, as I finish, I'll quickly go through. So I think this is really going to be the focus of those experiments now, making sure we've got a nice large sample of supernovae, but really well measured, so we can really tie down, is this dark energy changing with time or not? So these are some of the amazing things coming, and I'm going to just spend a minute or two on each one of these, because they've all got different strengths and different things that they contribute to the whole question of supernovae and dark energy. So I think I'll just start. So the first one I was going to mention is the Rubin Observatory, and it was nice to see that you have an event to watch the first look images coming on Monday. So this is going to completely revolutionize supernova cosmology. And you will hear a lot more about this on Monday, but the real key here is its large field of view. So it has this enormous camera. I think it's 3,200 megapixels, and that allows you can sort of tile a much larger area of sky when you have a camera that big. And this is the projection of the field of view of the Rubin Observatory on the sky with the full moon there. So I think it's something like 40 full moons equivalent, which is very large for a telescope of this size. The telescope itself is about 8 meters diameter, so it's not the biggest telescope in the world, but it is the biggest survey telescope like this with such a wide field of view. So it'll be able to scan the sky very rapidly. It can do essentially the whole sky that you can see from that observatory every sort of 3 nights. So then it will come back every 3 nights and just keep repeating the sky. And then the part that it can see obviously moves around the sky during the year, and it will gradually tile the whole southern sky and keep doing that year after year. So this is just going to be churning out supernovae at an incredible rate. I think they're saying something like 1 million alerts, like changes every night, will be announced. So they're not all new supernovae. Some might be changes of old supernovae that are brightening a bit more or changing in other ways. And some might be things moving. Some might be flaring stars or active galactic nuclei. But the data stream is going to be incredible. So I actually had a slide to mention the first look in case you hadn't seen about it, but definitely watch that on Monday. We'll be watching. I'm very excited about that. So Rubin Observatory will find lots of supernovae, but as I mentioned, we really need the spectra of them as well, because we want to measure their redshifts and we want to confirm their type. So one of the experiments that I'm very interested in, and Lancaster's brought into this, is called FORMOST, which stands for 4-meter spectroscopic telescope, and it's a refit of the VISTA telescope in Chile. And it's a very large multi-object spectrograph with lots of fibers. Now I'm going to just lose my pointer and start this little movie. So these at the top, you're looking at a bunch of fibers and the ends of these fibers, they're on spines, so they can move around, and you can align the pattern of these fibers with objects that you're interested in the sky and feed the other ends of the fibers into spectrographs. And so with this system, we'll be able to take 2,400 spectra simultaneously. So we're part of, in Lancaster and several other people in the UK, got together to design a project to follow up supernovae that the Rubin Observatory finds with this instrument. And this is going to be very exciting, I think. And luckily, they're both going to come into operation around the same time. So this is called the TIDES project, and I'm going to show in the next slide how Rubin and Foremost are going to work together. So I hope you can see this. So this was an animation made by my colleague Chris Frohmeyer, and what you're looking at is that the sort of bluey yellow colouring is where Rubin has looked as time goes on, and you can see it's observing each patch of the sky many times, and the whole pattern moves across the sky during the year. And then the red dots are where Foremost is going to be looking. And this is with no particular coordination yet between the two. We will try and coordinate them, but even if you don't coordinate them, just because the part of the sky that's visible from Chile on a given night is the same, they will generally be looking in the general area, same general area. So as time goes on, after about 5 years, we think this Foremost instrument will be able to get spectra of about 130,000 supernovae and their host galaxies. So this is going to be very exciting. It's a good way of getting redshifts for all those supernovae, which Rubin can't provide on its own. So that's one of the, well, that's two of the projects I'm very interested in, Rubin and Foremost. Another one is the Euclid mission, which I mentioned right at the beginning. That beautiful image I showed you was from Euclid. And this is a mission that was launched in 2023. And it's doing really well. It's planned to do a whole sky survey. It does about a third of the sky over a six-year mission. But the real key here, although again, it's not a particularly large telescope, it's only 1.2 meters. It is in space though, and it has a very wide field camera, not quite as wide as Rubin, but that combination of being in space and being above the atmosphere means we can get really clear images, but also over a wide field of view. So the idea here is that we'll get much better information about the host galaxies that supernovae explode in by looking at the way they appear with Euclid. So if I show you that on the next slide, I think you get a better idea of this. So this is just a zoom in on one tiny bit of one of Euclid's images, but I think you can start to see the quality here, although I haven't got a scale bar on there, but it's roughly similar quality to the Hubble Space Telescope, but over much, much larger areas of sky. So pretty much everywhere that the Rubin Observatory looks and finds supernovae, we'll be able to look at their environments, their host galaxies, with Euclid. And it turns out that this is very important because what's been discovered recently is that supernovae, although with their very good standard candles, they do have some dependence of their peak brightness on the type of galaxy they're in. And so if we can measure their host galaxies with better resolution and better quality, we should be able to make some slight corrections to those peak brightnesses of the supernovae and get even more accurate standard candles out of it. So that's something I'm really interested in, and I'm spending quite a lot of time working on that at the moment and preparing for when Rubin really starts. But we can already practice by looking at the host galaxies of previous supernovae. So that's what I've been doing recently. Okay, and then the last one I want to mention is the big one, the European Extremely Large Telescope. So this is a project I was also involved in, not so much now, but when it was first being thought about, this is something I spent quite a lot of time working on. And so this is a project being run by ESO, the European Southern Observatory, with international partners. And the project is to design a 39-meter diameter telescope. You may well have heard about this because Edinburgh is also very involved in this. The ROE in Edinburgh is very involved in this project. So this will be the largest optical infrared telescope in the world when it's finished, and it's not all that far off now. It's going to have adaptive optics built in. That's what these lasers that you can see coming out are for. Those are to create artificial stars that allow you to correct for the blurring of the atmosphere. So it should work at the diffraction limit of a 39-meter telescope over quite small fields of view. But I mean, that would really be a very impressive feat. If I say if it's pulled off, I'm sure it will. I'm sure it will work, but it will be very, very impressive. So something like this, although it won't have the wide field to find rare supernovae, once you've found one, you can follow up with this telescope and it will get incredibly detailed and deep observations of supernovae. So we'll be able to observe very distant supernovae this way and get back further in time. I'll just get that. So I got to visit the site in 2018. That's me standing next to just behind me. You can see there's such a ring, which is where the dome is going to be mounted. And you can get a feeling of the size of the dome from that picture there. Inside the ring, there are some diggers preparing the land for where the telescope mount is going to be. Now, if you look on the ESA website, you can see some pretty impressive images of this telescope. Now, this movie is something I downloaded quite recently. It's a time lapse of the construction. I'm not sure I'll show the whole thing, but just to give you an idea of where things have got to now, you can see that ring I was standing in front of is put my pointer back, as now, so we were standing where there were some office buildings that go around the outside. You can see them now in that image. That's where we were standing, and behind us was the ring where the dome was going to be mounted. So that now has a dome on it. The dome moves, it's fantastic. You can start to see the telescope mount being built inside the telescope as well. And you can get a feeling of the scale from the cranes and the vehicles around the outside. So it's really happening, and it's absolutely incredible. I just can't wait for this to actually take shape. And then, so you could go and see that yourself. I've just got a still image here in case the movie didn't work very well, but you can really see that it's taking shape. So the mirror is not there yet. It'll be a segmented mirror made of nearly 1,000 segments, but the support for the mirror is there and the frame for the telescope is there. And obviously the dome is taking shape with its shutters that will come and go, open and close. So I think I'll stop there. I think the prospects are looking really good. We've got this amazing suite of new instruments on the horizon. Some Euclid is already up there working. We're going to have many more supernovae and much better measurements of each one and their environments. And so I think we've got a really good chance with this new suite of telescopes in the next few years to understand what's happening with dark energy. I'm going to stop there.
Well, thank you very much indeed, Isobel. That's incredible to see and hear all of this activity, and where it started and how far things have come in a relatively short space of time. But perhaps I can start with a question of my own. And thinking about the original experiment, which was to kind of measure deceleration and ended up finding something else. Is there a chance that in this search for dark energy, we think that's what we're trying to find, that we'll actually find that we need to look for something else?
Yes, I think there's quite a big possibility of that. I think I mean, the thing that I mentioned before, that we've started to see hints that maybe dark energy is not constant. That's a big result, and it would mean that even the cosmological constant in itself was weird enough. We couldn't explain that. If we're now finding something that's changing, that perhaps brings into doubt, makes things even more complicated. And I think the more complicated things get, and the more we have to come up with new things to try and explain why things don't quite match, I wouldn't be surprised if really there's some other bigger explanation that will come along and solve it all. Well, that's kind of what I hope. I hope that a new theory really will explain it all. And I see my role and those of my colleagues, the observers, to get the observations as good as we can, so there's no wiggle room for the theories until there has to be a theoretical breakthrough that explains it all. So I think there's quite a big chance of that.
Fantastic, thank you. Will, I'll hand over to you now to MC the questions from both chat and from YouTube.
Excellent. That was an excellent talk there, Isobel. So we start, and if we start with our questions from Zoom. So if you want to unmute, just go ahead when I call your name. If not, let me know, and I will just read them out. So Jim Barron, if you want to unmute and ask your question, please.
Okay, thanks very much for the talk. As I understand it, energy doesn't exist of itself, it's a property of something. And so since you've got dark matter and dark energy, is dark energy thought to be some type of new elementary boson or force carrier? Or is it just no idea and we've just given it a name to be going on with?
I think that, yes, there are theories that it's connected to a particle in some way. I think to start with, it really was just given a name, and this sort of constant explanation that Einstein's cosmological constant fitted very well, but the physical explanation for that could involve maybe particles coming and going or some. But the problem with that, I mean, you may have heard of this problem that if you look at quantum field theories that predict that particles can create and spring into life and go back again, they predict that there should be some level of energy in the universe everywhere, but the value of that is 120 orders of magnitude off. So you may have heard of this, but that's the problem, and that's a massive problem. So that it may be something like that that's causing this, but if it was, there'd have to be some other theory that explains why it's so much smaller. What we observe is so much smaller than the value you'd expect from those sorts of theories. And then if dark energy is a changing field, then yeah, again, you've got to come up with some reason why it should change. So why should physics be changed, or the particles or whatever's causing this change their properties, or the balance of particles change? So it could be something like that, yes, but right now we don't know.
Thank you.
Excellent. And would Ian Smith, otherwise known as Norving, please unmute and ask your question, please.
Hi. You said that there will be follow-up observations to determine the type of host galaxy, and that would be used to correct the results. To what extent will those corrections be? Could it even cancel out the expansion?
No, I don't know. It wouldn't cancel it out, but it would. So definitely the main result that there is accelerating expansion, that's robust, doesn't really matter. It's not really sensitive to these effects. They only started to emerge when we have much larger samples of supernovae, and we're trying to sort of add more and more free parameters. So if you allow dark energy to change with time, and you have an extra thing you're trying to measure, which is the rate of change with time, these much more subtle effects, then it starts to matter. So I think we really need to get this right for the next generation when we're trying to tell whether dark energy changes with time or not. But it's not going to be enough of a change to make the whole accelerating expansion, the existence of dark energy, that's not going to go away from that.
Thank you.
And Morris, if you want to unmute and ask your question, please.
If supernova properties vary with type of galaxy, could they also vary over time with galaxy evolution? Do we know the various galaxy evolutions well enough to factor for it?
That is an excellent question. So that is exactly why we're worrying about this. I think if it wouldn't matter if supernovae depended on their host galaxy types, if galaxies didn't evolve, or if the balance of galaxies, different types of galaxies, stayed the same with time, it would all be fine. The problem is, if, as you say, if galaxies evolve, then the supernovae will be exploding in different environments at different times of the universe. So we absolutely have to be able to correct for this. And so what we can do, there are various ways we can do that. We can look at how differently supernovae behave in different types of galaxies in the local universe now, and kind of extrapolate and say, well, if I don't know, a supernova explodes, say, in a spiral galaxy, it has a slightly different brightness than that in an elliptical galaxy. We can measure that difference now, and then we can extrapolate back and say, well, the balance of spirals and ellipticals was different in the past, so we can make a little correction. So that's the sort of thing, but we can also check that it is behaving that way as we go back in redshift. Once we've got enough supernovae, as we will have in the future, we can actually look in different chunks of redshift at this effect at the, for example, we could just pick only supernovae that explode in elliptical galaxies, say, and use those at all redshifts, because we'll have so many to choose from in the future. So that would help us check whether our corrections are actually working. But it's a really good point. I think that's actually where the biggest effort is now focusing in terms of supernova cosmology research. It's this environmental dependence, really important.
That was excellent set of questions there and wonderful answers. We've had very good showing on YouTube with people watching live, which has been excellent. But there's no questions, so
Okay.
so I think that's it for questions, unless anybody has anything.
Very good. Very good questions. Thank you.
Okay, thanks, Will. I guess last call for questions. And if there are no further questions, we can all come off mute and give our thanks to Isobel in the usual way.
Thank you.
Thank you very much.
It's been a pleasure. Thank you very much for hosting.
My pleasure. Thanks very much indeed for your time this evening, Isobel. It was fascinating. It's set me up nicely for Monday's event.
Indeed, yes. Enjoy.
Look forward to seeing some people there. And if I don't see you there, everyone else see you when we return from our summer break. But remember, those